Mindsetters, welcome to today's Grade 10 Physical Sciences show. Today we have a special revision lesson on waves. We have selected highlights from lessons shown earlier in the year to help you with your revision. Please send us your questions and comments on Facebook, on facebook.com/learnextra, or on Twitter @learnextra, so we can help you revise. Don't forget to download today's show notes on learn.mindset.co.za, or you can click on the link on our Facebook page. Now it's time to get on with today's lesson.
So let's practice a couple. And we're going to start with a little question. Let's read it carefully and let's make sure that we've got all the details there. It says a boat out on the ocean experiences waves. So they're water waves. They're really just swells passing underneath it, lifting it 9 meters from the trough to the, 8 meters from the trough to the crest, and the waves pass every 7 seconds and are a measured distance of 10 meters apart from crest to adjacent crest. Adjacent means next to. So that was quite a mouthful. Guys, I get lost in these sort of things. Say the wrong number and think the wrong thing. So what I'm going to do is I'm going to draw a picture just to make sure that I've got everything right. So I recognize I've got some crests and troughs. And what it tells me is, first of all, the distance from the trough at the bottom to the crest at the top, that's a distance of 8 meters. Now, the next thing it tells me is that the measured distance of 10 meters apart from crest to adjacent crest. Now, it doesn't mean from this crest to that crest. No, they're not next to each other. But it's from this crest to that one, that's 10 meters. And in the same way, from that one, from that crest to the next crest is also 10 meters. And so on. I hope you get the picture. They're all 10 meters apart from each other. The very important next thing is it tells us that the waves pass every 7 seconds. Waves pass every 7 seconds and are a measured distance. So from the time it goes from that one to that one, that time, or from this bottom back to the bottom, that's 7 seconds. Okay. We'll come and take all that information and now try and use it to answer the question. Before we get there, what are the tricks that we're looking for? We're going to be applying the definitions. And the first thing that I see that could possibly be a trick, I must watch out. This is the distance from trough to crest. Halfway, that distance, which will be 4 meters, is going to be known as the amplitude. It's either from the rest position to the trough or the rest position to the crest. So already I'm starting to think about where the tricks are. The other thing that I know, this distance that they've given me of 10 meters from crest to crest, which is the same as from trough to trough, that I recognize is given this symbol of lambda, and lambda stands for the wavelength. Now remember, the wavelength can be from crest to crest or trough to trough, or we can even say it's between any 2 parts of a wave that where the particles are in phase. They're moving up and down exactly in time with each other. So it could be from that position to the one that's coming down again at that position. In fact, that's going up because it's going to meet the crest if the wave is moving from that side to that side. So they can be anywhere on this wave pattern, but they're in phase. They're moving in time with each other. Like you saw those little red and green beads. The green beads were in phase with each other. They were one wavelength apart. Okay, so now let's try and answer the questions. I've answered some already. What is the amplitude of these waves? Well, notice we knew that it was 8 meters from crest to trough. So the amplitude, A, is equal to the distance from the trough to the rest position. Now, you don't have to write this out, but I'm just writing it for you so you understand. Or we can say it's half the distance between trough and crest, which means it's half of 8 meters, which is 4 meters. So we've got that. I've illustrated it, and I think we sorted with that. Calculate the frequency of the waves. Now, guys, frequency. We need to define frequency. I say that frequency is the number of cycles or complete wavelengths divided by time. So it's a divide by time. How many whole waves are there per second? Okay? The unit for frequency in SI units is hertz, but it actually means the same as per second, which I can write as second to the minus 1. So please be aware of that and make sure that you've got it right. So we don't want the time it takes for one wave, one complete vibration. We don't want the time. We want how many of these in 1 second. Now, in some cases, you'll get 50,000 waves per second. That's a very high frequency. But in other times, you might get something like half a wave in 1 second, or a quarter of a wave, or a tenth of a wave, or 0.000001 of a wave in 1 second. Let's see what else we know about frequency. There is a relationship between, if I turn this around and I say, what is the time taken for a given number of waves or cycles? Cycles, we simply mean those movements of up and down, the particles moving from maximum rest position through the, maximum displacement through the rest position, maximum displacement back to the original. That's one cycle. So we're wanting to know what is the time divided by the number of cycles. This is known as period. Now, very important, what can you see about these two equations? Well, hopefully you can see that on this one, cycles is on the numerator, and this one, cycles, is on the denominator, and time is on, time over here is the denominator, and time over there is on the numerator. They've flipped. They're reciprocals of each other. So the relationship that I'm going to use is I'm going to say, I know that frequency is 1 over period. And what was the given period? Well, what information did we get given? We're told that for the wave to go from a crest over there to the next crest was 7 seconds. Look at what it said. Let's read it carefully and make sure that waves pass every 7 seconds. That tells me the period. Period is 7 seconds. So I'm now going to substitute in, and I'm going to say frequency is 1 over period, which is 7. The SI units is seconds, so the frequency is 1/7. If I want to get that on a calculator and just make sure that I've got it right, let's just close that one. We want the old calculator out there. We're going to take the fraction button and let's just put it in. Let's move the calculator to where we want it and turn off that so that it's not on, and otherwise that's it. That's what I want. There we go. We're going to go 1 over 7, and we're going to say what's the answer? It's 1/7 as a decimal, 0.1428. Round off to 2 decimal places, 0.14. So let me write that, 0.14. Now, what's the unit? Hertz. Agree? Yes, we've got it right. Next one. It says, assuming none of the conditions change, how long will it take for these waves to reach the shore 24 kilometers away? Now, guys, this is a little bit of a word problem, but what we need to be able to do is to take all the information that we've got and apply it. We want to know the distance is 24. We want to first of all be able to calculate the velocity. Do we know what the velocity is? No, not yet, but we know the frequency and we know the wavelength. So let's get the velocity or the speed of the wave, because we know that speed is equal to distance over time. And we want to know how long. So we want to get time, and we can substitute. So let's see, we've got frequency over there. Remember what I told you, this was wavelength, so I've got that. It's in meters, it's in SI units, and so I'm going to substitute. We've got 0.14 times 10 meters, which is going to give me a velocity of 1.4 meters per second. Now, let's take that and let's substitute in over here. What's the distance? The distance was 24 kilometers, but I must change to meters. Multiply by 1,000. 24,000 meters. We don't know what the time is. The speed, we're going to say, is 1.4. Notice I've substituted into the equation, and I'm now going to calculate for the time. Let's make sure we get it right. Time is equal to 24,000 divided by 1.4, and I'm not going to do that in my head. I'm going to rather use the calculator, and I'm going to say 24,000 divided by 1.4 equals, and my answer is 17142.8. I'm going to round it up to 17143 because it's in seconds. Notice this time is in seconds. 17143 seconds. Now you can leave it like that, or you can change it to minutes and hours, but it's going to be divide by 60, and don't leave it as a decimal. Make sure you convert properly. Some calculators have conversions from seconds to minutes to hours, and you can do it quite quickly. Okay, well, that's the first question. Shall we have a look and see if we've got time for one more?
I think we should take a net break.
No, I want to do one more.
Okay.
One more, and then we can do it, because this is quick. So, because we don't want to run out of time. So let's just do this one quickly, and we'll then do it. Two pulses move towards one another. Pulse 1 has an amplitude of 5 centimeters, and it moves from the left to the right. So that's pulse 1. Pulse 2 has an amplitude of -3 centimeters, and it moves from right to left. So guys, what I'm going to do is I'm going to take this one, and I'm going to change the color. So I'm going to do the one in green and the other in this kind of a brownish color, orangish color. Okay, so let's go quickly. We're going to say this one has an amplitude of 5 centimeters, and it's just a pulse like that, and it's moving from left to right. And this one has a amplitude of -3. Now, I haven't got a scale here, but I'm going to just approximate it like that, and it's moving in that direction. Okay, makes sense. We'll say, when we say, why did you draw it like that? Well, that's negative. That distance there is -3 units, centimeters. If I was on a grid, then I would draw it like this. This one, I'm just sketching. This one is 5 centimeters above. Now, what it says, draw a sketch to indicate these pulses relative to one another, and that's what I've done. It then tells me the following. It then asks me, identify the type of interference that will occur when the pulses meet. Now, look what's going to happen. If I take this one, and let's move it, and that one, and I move it there, what's going to happen? Remember, that's down 3, that's up 5. I'm going to be left with a new thing. At that point, that's going to be a +2. I'm going to just draw it in a different color. But it's got less. It hasn't got bigger than before. It's got smaller. So this is destructive interference. This is destructive interference. And the last part of this question, I think, now there's one more, is calculate the amplitude of the resulting pulse when the two met. Well, we've done it already. It's going to be plus 2 centimeters. We use the principle of superposition. Very important principle, superposition. We say what's happening is the one is going, the particles are being pushed up by 5, the others are pulling down by 3. Add the two together, negative 3 plus positive 5 gives you positive 2. And that's where we get the answer. And then the last one was to draw the picture when they passed one another. Well, I'm going to cheat. I'm just going to take my fancy pen on this lovely smartboard, and I'm going to move them into the positions they were. So this one started, the orange one started on the right, it's now on the left. The green one started on the left, and it's now on the right.
Okay guys, I hope you're enjoying this revision session. If you are struggling and need help, please post on the page or submit your questions to the Learn Extra Help Desk. Now it's time to take a quick break, so don't go away. We'll be right back. Welcome back from the break. Remember, if you need to revise any other topics, you can get the notes and watch all the videos from the Learn Extra live shows on learn.mindset.co.za, or you can subscribe to our YouTube channel, youtube.com/mindsetlearn. You'll find that we've organized all the videos into shelves and playlists to make it easy for you to get what you want. Now it's time to get back to the revision.
Here now I've got a set of questions that we're going to go through, and we're going to practice through them together with me. So make sure you sit, you have your book, you have your pen, you have your calculator, you're a science learner, and therefore there's no way that you're going to have that Spazzer Shop calculator with you. You have got a beautiful scientific calculator with you that you are using.
I feel like I should jump in.
Really?
I feel like I should jump in and tell the mindsetters that if you're using that Spazzer Shop calculator, worry not, because next week we're having a competition that is kickstarting from Monday. It is proudly sponsored by Casio. So we'll be giving away calculators.
Beautiful, beautiful. So stay tuned, stay tuned. Part of these lessons all the time. Now let's come to our question here. The first question under improve your skills. So we'll be learning on how to work out solutions to problems based on sound questions or wave questions. Let's have a look at this one here. Question number 1. A guitar string produces a musical note, and the E, this is an E note, all right? And thus travels through air at a speed of 330 meters per second. The frequency of the note is 329.6 hertz. Calculate the period of the note. Now, look, you are to calculate for the period of the note. By the way, what is the symbol for, the scientific symbol for period when we're talking waves? It is capital letter T. So you write your capital letter T and you say it is equal to. And what is that equation or that formula that gives us the period of the wave? When we have, look what you are given here. You are given your frequency, you are given the speed of the waves, of the sound wave in air, all right? Now, period, you must know, it is always given by 1 over F, okay? 1 over frequency, all right? So what is 1 over frequency here? Our frequency is 329.6 hertz, or per second, if you like, all right? Because a hertz is an equivalent unit for per second, all right? So then that works out to, no, you don't have to crack your skull about this. You bring your calculator on and just say, okay, I've got 1 divided by 329, 329.6. And what is my answer? And you find that to be 0.003, all right? So that is 0.003, 0.003. 3 what? Remember, you are dividing by per second. So this is second. Period is measured, it's time. it is measured in seconds. So this is 0.03 seconds. Okay? Just putting it in full so that you don't mistake my S there for 5. It's 0.003 seconds. All right? That's your period. Don't forget this formula here. It's critical when we're talking waves. Right now, the next question is find the wavelength of the note. Now, the wavelength is lambda, that symbol there. And because we are given the speed in which the sound wave is moving in air, and we are given the frequency, we can actually go straight to the wave equation. And what is that wave equation? You must remember it. The wave equation is V equals F times lambda. This is your wave equation. All right? And we are given the V is given to us as 330 meters per second. And the lambda is, the frequency is 329.6. So all we need to do is to substitute into this. So 330 meters per second equals to 329.6 times lambda. Therefore, we can find what lambda is. Lambda will be 330 divided by 329.6. All right? And what will that be? Again, you bring your calculator. All right? We've got 330 divided by 329.6. And what's the answer? We find lambda, which is the wavelength, to be 1.0 meters. Okay, remember that wavelength lambda is measured in meters because it's a distance between two consecutive points that are in phase in a wave. Okay, good. Now, moving on. A different string on the guitar also produces a note. So I'll put that here. Also produces a note with a frequency of 82.41 hertz. And this note is also an E note. Can I have an E note with different frequencies? Yes, because I can have different pitches from different strings of a guitar. Okay, so the pitch of one string may not necessarily be the same as the pitch of the other string, but they may be working on the same note. For example, your thicker strings on the guitar versus the lighter ones, thin ones, they won't produce the same pitch for the same type of notes. All right, so that is where it comes from. Then the question here is, you have got 82.41 hertz for your the second string there on your guitar. All right? What can you deduce about these two notes or these two strings? Okay? These two strings, sorry about that, which produces the same note. Okay. So what is happening here is that you have got the first one that we spoke about. The first string produces a higher pitch. Why? It is producing a higher pitch because it has a higher frequency. Okay? If you remember well, the frequency that it has is the 329.6 hertz. Now, this is much higher than the second one. Okay? So this is what we are deducing from this. So I can also say that for the second one, the second string produces a lower pitch. Okay? Why? It has a lower frequency. Okay, so lower frequency, lower pitch. Higher frequency, higher pitch. And you can see that the frequency that we are given here for the second string is 82.41 hertz. Now far, far lower compared to the 329.6 hertz, which was the first string that we looked at. Okay, so this is very important. The main idea here is to link frequency to the pitch of sound. Now, there's also this one that I need to quickly talk to you about before we move on. Whilst you link frequency to the pitch, the loudness of sound is linked to the amplitude of that sound wave. Okay, so whether a 2 centimeter amplitude of a wave would not be so loud compared to one that is 5 centimeters. Okay, so the 5 centimeter one will be much louder. The amplitude, remember the amplitude? That's what the loudness of the sound is related to. Right. Moving on to question number 2. A teacher uses a signal generator to produce sound waves which have a frequency of 10 hertz. So we've got 10 hertz frequency and a wavelength of 40 meters in air. The signal generator is attached to an oscilloscope. A wave pattern is displayed on the screen with an amplitude of 2 centimeters. Remember what I said about the amplitude? Relates to the loudness of the sound. The oscilloscope is adjusted to show 2.5 seconds. All right? Now 2.5 seconds, draw a sketch graph showing what you would see on the screen. Now if my frequency is 10 hertz, it means I've got 10 complete waves. I've got 10. I've got 10 complete waves passing a point in 1 second. Okay? So let's go back to this. 10 complete waves passing a point. In 1 second. So if I have a time interval that is given to me to be 2.5 seconds, how many complete waves am I going to have there? In 1 second I've got 10. It means in 0.1 second I would have 1 complete wave. Okay? 1 complete wave. So in my graph here, if I were to draw, so let's come to the question here. It says, draw a sketch graph showing what you would see, what you would notice on the screen. All right? In my graph here, the amplitude has to be 2 centimeters. So I would have 2 there, and then my minus 2 centimeters there. So that is my maximum point. Okay. So at 0.1, I would have a full wave. 0.2, 0.3, 0.3. Oh, sorry. So I need to make this longer so that we can have a nice shape coming up here. Okay, so allow me to have my 0.1 there and my 0.2 here and my 0.3 there. Okay, so halfway in between will be my 0.25. In fact, okay, so in this 2.5 seconds should have been 0.25 seconds. Sorry about that. So let's put it like that so that we can have a shape, a nice shape of our graph here. Right, so drawing that graph, I have a complete wave here, all right? And I would have a complete wave there. And obviously when it's 0.25 and a half, I will have something like that, okay? Pardon my drawing there, but this is a neat wave. Look at it as a very, very neat wave as it is. Now, that's what I will see or perceive on the oscilloscope, on that screen. That's what will be happening. The next question here, which is question number B, says, on the same set of axes, draw a graph showing a wave that has double the amplitude and half the frequency. Double the amplitude and half the frequency. All right, now, if it has got double the amplitude, it means it will come to some point here where you have, say, it will be 4 centimeters. Okay, so this would be up there. And you will have a wave, it's double the amplitude and half the frequency. When you halve the frequency, you double the wavelength. So what it means is that I would have my wave this time going like that. I need to bring my, let me just do that. So I'll have my, what was a full wave is now half the wavelength. Okay? Half the wavelength, like that. And obviously, it would have gone much down this side as well. Look at it. Because it must go to 4, come back there, and then it goes up to 4 as well. But it can only go to that point there, which is the point of 0.25. So that's what I would have if we double the amplitude and half the frequency. This is the shape that we'll see or perceive on the oscilloscope. All right. All right, and the next one says, calculate the speed of the sound wave. Now, this is easier. You go back to the wave equation, as I've told you. Now, V will be equal to, remember we are given frequency. Frequency is 10, and the wavelength is 40. And therefore, the speed of the wave is 400 meters per second. That's what it is, okay? Quick and straightforward with that one. Don't forget, like I said, with the other equations, the period. Don't forget your wave equation. It's very critical for you to know and use at this stage. Okay, now quickly predict what will happen to the speed of sound when the sound moves from air into still bar. Look, with air, we have got particles that are far apart. With a still bar, we've got particles that are closer together because this is a solid. So what will happen to the speed? The speed of sound will increase. Okay? Moves faster in solid. Moves faster in solids. Okay, so Don't forget that. What will happen if the sound wave moves from air that is moves from air, normal air in that speed to an air that is 5 degrees cooler? Now look, if it is cooler, you have got less kinetic energy, okay? Molecules move slower, so molecules move slower, all right? And when molecules move slower, that means the speed of sound decreases, okay? Now, this is the issue of temperature. The higher the temperature, the faster the sound in that medium. The lower the temperature, the slower the sound movement in that medium.
I think it's time for a break now, so go do a few stretches, take a deep breath, but don't go too far because we'll be right back. Welcome back from the break. Remember, if you have any questions, you can submit them to the Learn Extra Help Desk. You'll find the details pinned to the top of the page. Right now, let's do some more revision.
So let's get going. 2 forms of radiation are given. EM radiation with a frequency of 0.5 T hertz. Well, what is that T standing for? That T is standing for terahertz. And you might have heard of maybe a terabyte in terms of kind of computers. Tera is standing for a very large number. The tera stands for times 10 to the power of 12. Remember I said we're going to deal with big numbers. And the hertz is the unit for frequency. EM radiation, another form of radiation, B, EM radiation with a wavelength of 890 micrometers. Notice a wavelength is a distance measurement, and they're giving this micro symbol, and micro stands for times 10 to the power of -6. So that's a very small distance. Okay? Calculate the energy of a photon of each form of EM radiation. So I'm going to do them separately. We'll start off with A, and I was working in blue. So A, I'm going to work energy is equal to H times F. That's the energy of a photon. And the H there is standing for Planck's constant, which is 6,63 times 10 to the -34. I'm putting that in brackets. And then the frequency was 0.5 terahertz. So 0.5 times 10 to the power of 12. Okay? So critical that you know what those prefixes mean, these little subunits. Okay? Now I'm going to go across to my calculator and we can write those in. 6.63 immediately the times 10 to the button, and it's -34 multiplied by, and I'm going to actually just put this in brackets, so let's zoom across to the, if it will let me. I'm just going to clear it and do it again. 6.63 times 10 to the -34, close brackets, multiplied by, and it was 0.5 times 10 to the power of 12, close brackets, equals. There's my answer, 3,3. I'm going to round off to 3,32 times 10 to the -22. And notice it's giving you your answer in the scientific notation. So let's write it down in that scientific notation. And 3.32 times 10 to the power of -22. I'm just going to undo. Oh, maybe redo that. Or not. Sorry, I've jumped across. There we are, -22. Let's just try and clean that up. and have it written easily here, negative 22, because I definitely want you to be able to see those that scientific notation. What's my unit going to be? Well, it's an energy value, so energy is measured in joules. The next one, B, and I think I'm going to do this towards the bottom of the page so that I've got some more space. And I'm going across to green. And B's answer was, well, it was also energy. And so you could say, well, I want to work with HF, but was I given the frequency? No, I wasn't. I was given the wavelength. So I'm going to write down wavelength. And I want you to identify that we can, and it was 890 micrometers, which is 890 times 10 to the power of negative 6 meters. I want you to notice that we can actually, we have an equation that we can go straight into here. But the equation comes from somewhere. And the equation is based on the same equation. We have energy is equal to hc over lambda, which is the wavelength. Well, why is that? Well, the reason for that is because you may have come across c is equal to frequency times wavelength, okay, where notice this is velocity is equal to frequency times wavelength. We've had that many times in the last while as we've done waves and longitudinal waves and transverse waves. But the speed we're dealing with here is the speed of light, the speed of all electromagnetic radiation. So we've given it the symbol c, which is 3 times 10 to the power of 8 meters per second in a vacuum. And so what I'm actually doing is I'm rearranging this equation and I'm solving for f. Okay? So if I'm solving for f, it would be c divided by wavelength would give me the frequency. So coming across here, I've actually got the exact same equation as is written there, but instead of writing f, I'm writing, well, let's just take this part away so that you can see where we're coming with it. H times, not frequency, but c divided by wavelength, which I can write simply as one quick equation and write that as hc over lambda. So substituting in, we've got very quickly 6.63 times 10 to the negative 34. The c I said was the speed of light, or the speed of all electromagnetic radiation, which is 3 times 10 to the power of 8. And that's divided by the wavelength, which we'd written at the top here, was 890 times 10 to the negative 6 meters. Notice how important being able to write quick answers in scientific notation is going to be here. So cross to our calculator. I'm going to clear this answer. 6.63 times 10 to the negative 34. Multiply that by, it was the speed of light, 3 times 10 to the power of 8. I'm going to do my top line first, and that whole thing would be divided by 890 times 10 to the power of negative 6. And I get my answer 2.23 times 10 to the power of negative 22. Although we've got all these other digits, I'm going to round off to the second decimal place. So 2.23 times 10 to the negative 22. And going back here, it was 2.23 times 10 to the negative 22, my units, joules. So I think we've answered A. Calculate the energy of a photon. We have indeed. That's done. The next one, part B. Compare the forms of radiation in terms of which has the longer wavelength. So when we speak about wavelength, recall we're dealing with the distance of one complete wave. Okay? And as you consider the distance of one complete wave, you're thinking through things like well, what is its energy? What is its frequency? Those can certainly help you. And a quick thought here is high energy is going to always have high frequency. And because these things are related based on the C is equal to frequency times wavelength, the speed of light is constant, so that C is staying the same. The frequency, if the frequency is high, the wavelength must be low, or the wavelength must be short, would be a better word to use. So looking at it, I can immediately, just by looking at the energy, say which one has a higher energy. The one with high energy is going to have high frequency and therefore short wavelength. So quickly looking at it, what were my answers? This one was high energy, okay? And so I could say here, therefore, high frequency, low wavelength, okay? Which one has the longer wavelength? It must be this one, B, and you could work that out, okay? How could you work it out if you really wanted to? This one, we were given the wavelength, B's wavelength, and so I could go back and work out the wavelength here would be wavelength is equal to C over the frequency. So I could go and work that out, and it would be 3 times 10 to the power of 8 divided by 0.5 times 10 to the power of 12 terahertz, and we can get our answer. So 3 times 10 to the power of 8 divided by 0.5 times 10 to the power of, was it positive 12. So 3 times 10 to the power of 8 divided by 0.5 times 10 to the power of 12. And that gives me an answer which is 0.30. 0.0006 meters. And so you could go and compare that in terms of its wavelength, because remember that was the other wavelength. So you can compare them. Let's turn to our next question. We'll see how we go with this. I'm just going to clear these scribbles. X-rays, also part of the whole electromagnetic spectrum. It is given that the wavelength of certain X-rays is 2.3 nanometers. Now immediately I'm writing there, wavelength is equal to 2.3 times 10 to the power of -9 meters. Remember, very important that you go and learn what those little values are referring to. Nanometers, terabytes, tera, etc. Calculate the frequency of the X-rays. Now I've done a similar question a moment ago. We have C is equal to frequency times lambda. I always write the original equation first, and then you can go and play with it. What have I got? I'm trying to find frequency. So frequency is by itself is going to be equal to, well, speed of light divided by the wavelength. And that's 3 times 10 to the power of 8 divided by 2.3 times 10 to the power of -9. Now, I want you to note that negative is important, is equal to. So, calculator. Again, we're using this scientific notation. 3 times 10 to the button, power of 8, divided by 2.3 times 10 to the power of -9 equals. That's my wavelength, that's my frequency, 1.30 times 10 to the negative, times 10 to the positive 17. So 1.30 times 10 to the positive 17, and the units here would be hertz. Okay. Now recognize that that's, and I always try and do this, recognize that that's quite a high value, and X-rays do have high energy. That's how they have such an interesting penetrating ability. Determine the energy of a photon of this X-ray radiation. Well, once again, E is equal to H times frequency. that was 6.63 times 10 to the negative 34. Multiply that by my answer previously, 1.30 times 10 to the 17. And I can get my answer. Calculator, 6.63 times 10 to the negative 34. Multiply that by 1.30 times 10 to the 17 equals, and we get our answer here as 8.62. 8.62 times 10 to the negative 17, and it would be joules. Check it quickly. 8.62 times 10 to the negative 17 joules. Good. And that's part B. Suggest a medical use for X-rays. Now I'm just going to answer this. I'm not going to write it down specifically, but think through. X-rays we use to detect broken bones. If you break an arm or leg, you would go and have an X-ray, and the doctors would be able to diagnose that broken bone. So, broken bones can be detected. Okay. Discuss the penetrating ability of X-rays. X-rays can penetrate through our skin and through our muscle layers, but they can't penetrate through bone. So, they can penetrate quite deep, but not through our bones, which is how we can detect broken bones. What precautions would medical personnel operating X-ray machines need to take? Now, you or I don't often go for X-rays, and we don't often break bones, hopefully, so we're not going to be exposed to huge amounts of this radiation. But a person operating an X-ray machine, a radiographer, would be standing there with the X-ray being all the time, on a daily basis. It's their job. And so they would usually wear an apron that is lined with lead that would stop the X-rays from going any further. Or very often what they do is they position the patient and then they walk outside the room, and the walls or behind a screen, which is also lined with lead, that would protect their bodies against that radiation. Because of course, over a period of time, radiation can be damaging to a person's body, particularly high energy radiation. And so that could be a concern.
We've come to the end of today's show. Thanks for joining me and for chatting to me during the show. Remember to visit our website, learn.mindset.co.za, to download the show notes and to watch all the videos from this year's shows. Goodbye.